Okay, so we're going to continue with the material for this class. And now we're going to go into a new chapter about plate bending. Okay, so it's going to be quite a difference from the previous chapters. Okay, so be ready. Okay, let me share this. Okay. Can you confirm me, Isaac, that you're watching the whole thing?
Yes, doctor.
Okay, so these are the topics of this chapter, 4 sub-chapters. It will take us about 2.5 weeks, more or less, okay? Today, we're going to start the deduction of the equation, bending equation for isotropic plates, okay? And then we're going to solve this in one specific case. And this is the case that I want you to analyze, okay? So it's going to be simply supported on all the edges, rectangular plate, and the load can be anything, okay? As a matter of fact, the most interesting load is the concentrated force that we're going to be applying in the lab the next Friday, okay? Now, to reach this, we have to take an intermediate step, and it's this one here. So we're going to take the simply supported rectangular plate, but the load will be sinusoidal, right? Okay, so in here, we're going to have some, we're going to have something like plate, but the load would be something like this, sinusoidal in both directions, okay? So you see that in one direction, you have a full cycle, and in the other direction, we have half cycle, but both are sinusoidal, okay? So we're gonna solve this in 4.2, and we are going to use this in order to complete solutions for arbitrary loads, okay? And finally, you see here that this word is different than this one here. Here we analyze, here is just the description of the solution for the clamped case, okay? So in this case, 4.2 and 4.3, all these edges will be simply supported, okay? In this case, in 4.4, we're going to consider all the edges will be clamped, okay? It's a bit more difficult, and the problem is that we don't have the time to describe this solution, to analyze this solution. So instead of solving this case, what we're going to do is simply to describe the solution, okay? And in the case of Timoshenko's book, they present the solution in general, and the case that we want to analyze, this one here, okay, is the case where we have a concentrated force in the plate, and we can apply Timoshenko's solution for this case, okay? So 4.2, 4.3 are analysis. 4.4 is just a description of the solution. Okay, so here we're going to take the differential equation and we're going to solve it. We're going to be careful with the boundary conditions and all of that. Here is just a description because it is longer process and we don't have the time to describe or to analyze in detail. Okay, that's that. Some basic terms here that we are going to be using quite often. So partial derivative, in this case, in general, the deflection, we're going to call it W. But this W will depend on X and Y. Okay, so since we have these two are independent variables. Okay. In the past, we call it dV dx in previous chapter. Now we're going to transform this into partial of W with respect to X. Why? Because there are two. Okay, so in this case, I'm insisting that I'm changing only one variable and the other keeps constant. Okay, So we have to be careful with that. Isotropic. Do you remember what does isotropic mean? Does anybody remember what isotropic means? Anybody? Anybody? What's the meaning of the word isotropic? No? Okay. It means that, for example, if we take a plate, okay? Take a plate like this, and we take a piece of this plate, this, and another piece like this, and another piece like this, okay, and transform those into specimens, okay, and take any one of them. You remember this from the solid mechanics course, okay? And you clamp it and pull it, clamp it and pull it, okay? And from here, you get E, you get sigma Y, sigma ultimate, and things like that, okay? If you take this plate and take these pieces, these specimens in any direction and do this test, the result is going to be the same. That's why this word means iso. Okay, so it's the same behavior in any direction. That's the meaning of the word isotropic. Okay, uniform. Okay, that means that in any point, in any position. Okay, so here, 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 or in here. For example, we're going to say that the E has a constant value. Poisson ratio has a constant value because we are assuming that the material is uniform. It's an assumption. It's never really uniform. Okay, there are some variation. For example, you will be able to measure the thickness of the plate, and you will find that there are some differences. Okay, it's small, definitely, but it's not constant, it's not uniform. But we assume that it is uniform, okay? So there. In the thickness, you know, it's this dimension here. And we call it usually T, okay? You see immediately that the thickness, in this case, this dimension, is much smaller than the other two. And that will lead us to certain simplifications, okay? So I think these are the basic terms that we're going to need. There are many other terms, but we have already employed from previous chapters, so there's no need to redefine them here, okay? So let's start by deducing the bending equation, okay? Now, let me write here, just for the sake of comparison here, for the beam, what was the equation for the equilibrium beam equation? It was E I sub C B comma 1, 2, 3, 4 is equal P of X. Okay, so in this subchapter 4.1, we're going to deduce an equation similar to this one, but remember that in this case, we're going to have independent variables. So it's going to be a little bit longer, but the shape of the function of the equation, you will see at the end, it's quite similar to this one. Okay, so let's do it. Now, before we start this chapter, the question is, why do we need to study plate bending? And you see here the general structure of the ship. And you can see immediately in how many places do we have plating. Okay, so this is something that it's a good idea to show here. This is the deck, and you can see that the ships are built in this way. Okay, and each one of these is what we call an strake. Okay, in Spanish, I think it's a adaptation, and we call it a traca. You see that this is a traca, the stringer straight, and you see that on the side, each one of these is a straight, and the top is what we call the shear straight. This is the stringer straight on the deck and the shear straight on the side. Okay, and usually these two straights, because we have a decent high shear stress and a very high normal stress, so usually we increase the thickness of those two straights. Okay, we have a bulkhead, and you see that the bulkhead supports pressure in this direction, normal to the side. And here we have these elements. Okay, these are frames. Okay, transfer frames, longitudinal frames, and we have the keel here, thicker. So you can see that immediately there are many plates that we need to analyze. Okay, for example, we can take some of these here, and we can assume that there's going to be some loading. Because of this loading, it's going to deflect. How much it deflects? What are the level of stresses that they develop? That's something that we need to calculate. Deflection, stress, we need to calculate that. Okay? Now, before we go on, okay, that's something that we need to differentiate. Okay, we're going to have a plate. Okay, in a minute, we're going to include the reference system. Usually this is X, this is Y. Question, Z points upward or downward in this case?
Downward.
Yes. So it's X, Y, Z points downward. X, Y, Z. So yeah, Z points downward. Okay. And in this chapter, since this is bending, the loading will be like this. So it's going to be normal to the plate. So this produces bending. Okay? This is the problem that we're going to analyze in this chapter. Okay? Let me change color. There could be another option. For example, what happens if I apply a force like this? Okay, you see that this F that I have drawn here, it's in the plane XY, has components in X, components in Y. Okay, this is in plane loading. Okay, usually we call this plane stress. In green, plane stress, that is not what we are going to study. In blue, dark blue, bending, lateral load, that is the case, that's the situation that we are going to analyze in this case, okay? So that's why we call it clearly. This is plate bending, okay? If you want to analyze in-plane loading, yeah, we can do it, but we don't have the time to do it in this semester. Okay, so it has to be very clear. Similarly with the beams, we have a beam, we have a load like this, right? If we have something like this, that's what we call a truss. Loading like this, deflects like that, that's a beam. We're going to analyze beam plate bending. Okay, let's go. So there are some general characteristics of this plate that will allow us to do some simplifications, okay? First, the thickness is very small compared to the other two dimensions, okay? So in general, we're going to be working with rectangular plates. So we have this is A, this is B, and this is T. I will say here, the thickness is going to be much, much smaller than A or B. Okay, now, if we consider that, okay, let's do a big zoom. Okay, so let's try here, zoom. So this is the thickness. Okay, up here, tau is 0. Why? Because it's open. Down here, tau is 0 because it's open. So this, let's suppose this is X and this is Z. Anybody can help me? What are the subindices of this tau? Mr. Villalba, what are the subindices of this tau? This on this surface. Mr. Villalba, please.
X and C.
Mr. Villalba, I can hear you.
X and C are the
Oh, it's ZX.
Yes.
Why? Because this is normal to the Z-axis, so it's Z. And here it points in the X direction, so it's ZX. Now here, this is tau XZ, yes. And it is 0 because the other is here is 0. So these two are equal, 0. Similarly here. Now, T is small, so we start here, increases, and we have to come back to 0. But this is very small. Okay, so you start in 0, increase, but you have to go back to 0. So basically, this is very small. So we neglect it. So we're going to say something similar to that. So we're going to say that tau XZ is that, tau YZ is that. And we assume that sigma Z is much smaller than sigma X or Y, and we also neglect it. Okay, so because the thickness is very small, tau XZ, tau YZ will going to be neglected. Sigma Z in general is much smaller than X or Y, so we neglect it. So we're left only with 3 components, okay? Stress tensor, sigma X, sigma Y, and tau XY, okay? That in mind. So that's one thing. Another thing is that this is something that we said before, the deflection. So let's suppose that we have a plate here and we have a load here. Because of this, it's going to deflect. So here I have, but the problem is that I have 2 directions. And you can see immediately that in this direction, it's going to be the change of W in the X, I'm sorry, this is Y. This is going to be dW dx. But also, you could calculate this slope. And this is going to be partial in the Y direction. So from now on, in this chapter, remember that derivatives are not something like this. They're going to transform into something like this. Okay? So, for example, when you say shear force, that's incorrect. Why? Because we have two shear forces. When you say bending moment, now you have to tell me it's either bending moment in X or in Y. Okay, so we need to be more specific because the two directions are very important. Okay. And finally, there is another thing which is very important, is that in general, the amplitude of the deflection is much smaller than the thickness. Okay, that this is the amplitude of W, and this is the thickness. Okay, that means that the two problems are separated. Okay, so let me draw one plate like this. Okay. There. So let's apply a force, a load like here. So it's going to deflect, right? So we're going to show the deflection like this. There was a noise. Okay. Now, by simple common sense, right? What happens when you do this? What happens is that this point will try to move in the horizontal direction, right? This push here, and this end will move like this. But since we are assuming that W is very small, then this motion is neglectable. Okay. Engineer Isaac is doing his master thesis. And in that case, we cannot assume this. The deflections in his case are very large, extremely large. And the result is that in this case, in his case, the lateral is coupled with the in-plane. In our case, no. We assume that what we do in this direction is not coupled with what happens in the other direction, are uncoupled. Why? Because W is small. So bending is uncoupled with in-plane response. Okay. Now, in general, you see that we do something like this, right? You see that the deflection here is extremely large, right? It's just an optical illusion. If I draw a very small deflection, then you will not be able to see the some details, physical details. That's what we have to show with very large amplitudes. But in general, the amplitudes are going to be very, very small, neglectable. Okay, so small that I have a plate, I apply a force, and basically you don't see the difference between the deformed and undeformed. Okay, but the problem is that if I consider that and I try to explain something, it's going to be difficult to understand the implications. So that's why we have to draw a very large deflection, but it's just an illusion. It's just to be able to explain things. In general, this is right in this chapter. W is very, very, very small. Okay? Finally, people, please listen to me. There are zillions, there are many books about plate theory. Many, 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 many books. Each one of them uses a different notation. Each one of them uses a different symbology. Each one of them uses a different sign convention. Suggestion: stay with the class notes. I try to be consistent with symbology, terminology, sign convention. If you start here, do not understand something, and jump to Timoshenko, there are many books, you're gonna get confused. Stay with the class notes, otherwise you are going to get confused, okay? Said it as clear as I can. Please stay with the class notes. There's something that you don't understand, come to the office hours, send me an email message. You don't trust me, send an email to Isaac. Okay, but don't start jumping from reference to reference. It's very difficult, very dangerous. Okay, I can do more. I cannot do more than that. Okay, now let's describe in general what we're going to be doing. We're going to do three steps. Okay, first, we're going to relate the bending and torsional moments with curvature. And here, you remember when we did this in the case of the beam, okay, we used the kinematic hypothesis. And we're going to do something similar in this chapter. We're going to accept that if you have a thickness like this, and it bends, this section is just rotates. And that will allow us to describe the strains with a very simple relation. Then we assume that the stresses follow Hooke's law, so the stresses will follow a linear relationship in the thickness. And that's the result of this kinematic hypothesis. That will allow us to relate moments with curvatures. Curvatures, second derivatives. That's the first step. The second step, equilibrium. Okay, we're gonna take a small element, right? And we're gonna take forces, moments, bending, but also torsional moments. And all of this has to be in equilibrium, okay? So remember, this equation is for one arbitrary element, very small element. If we find a solution, that means that any element in this plate is in equilibrium. If any element is in equilibrium, that means that the whole plate is in equilibrium. And then the third step is just to combine. So we combine the first two steps and we end up with the partial differential equation. I'm not going to write it here. We're going to do next session. Partial, linear, and coefficients, order, non-homogeneous differential equation. Okay, and we have to solve it. Since it is linear, that's the most interesting thing. We can apply combination of simpler solutions to find a more complex situation. Okay, at least let's get started. Okay, so let's go for the first step. The first step is we're going to relate bending moments, torsional moments with curvature second derivatives. Okay. If I ask you, for example, let me ask somebody. Mr. Tenemea, in the case of the beam, what's the relationship between bending moment and curvature? In the case of the beam.
Is the E by, o sea, the Young modulus by the inertia and the second derivative of curvature,
It's equal to?
the bending moment.
Exactly. Something like that, we're going to reduce in the first step. Thank you. Thank you, Mr. Taname. Okay, so one of the first things that we have to agree is the sign convention. People, I myself have bad memory, okay? So what I have to do when I have bad memory is just repeat these things one or several times until I learn it and I put it in my memory, okay? Okay, so this is x-axis, this is y-axis, and the vertical z points downward. This is the system that we're going to be using. Z points downward, okay? Now, in this case, this is the positive x phase. Positive x phase. This is positive y phase. Okay, so in the positive x phase, this is the shear force. I'm sorry, I cannot see this. This is Qx. Okay, so positive shear force Qx in the positive x phase points in the positive z direction. Similarly for the y case, this shouldn't be here. Okay, so this is mx. This is bending moment. People, be careful, okay? Because in this case, we have bending moment and torsional moment. So please, with your thumb points in the y direction, and this is the bending moment, mx. This is in the y direction. This is mx. Okay, now your thumb points in the x direction, and that's the torsional moment. This is mxy. Okay, this here is mxy. Okay, so on this phase, positive x phase, you have shear force, bending moment, torsional moment. Okay, in the positive y phase, we have shear force, we have bending moment, y, and we have torsional moment. So this is myx. Be careful. In this case, in the y phase, the thumb points in the negative x direction. Points like that. But that's a negative direction. In the case of the x phase, points in the positive y direction. My, mx. Okay? And finally, in the y phase, your thumb points in the y direction, and that's your myx. This is yx. Okay? In this case, this is the external force. And the external force in this case is going to be expressed as force per unit area, not per unit length. Per unit length was in the case of the beam. In this case is, okay? In the other sides, okay, you have negative phases, and all of these internal forces change its direction. Sorry, change their sense. Okay, shear force, instead of pointing downward, it point upward, etc. Okay, please take a piece of paper, write this, and then include the positive directions. Please do it. Okay. Now, on the left-hand side, okay, since this is Z, okay, for example, this is the X direction, this is Z, okay, this is a slope, and the slope is increasing, right? So that means that this is positive curvature. And that's what we're saying here, okay? We're saying that this is positive curvature in the X direction. And similarly, this is positive curvature in the Y direction, okay? So if you have a plate like this and ends like this, okay, that's positive curvature. It bends like that, that's negative curvature in the X. And similarly in the Y direction, that's positive, that's negative. Okay, please take a paper, write it down 1, 2, 3 times until you learn it, you put it in your memory. Okay, remember, the next evaluation will be closed book. Okay, so this is not equilibrium. Please, in your class notes, it is incorrect that we include the changes, okay? In the second step of this procedure, we are going to include the equilibrium. We are going to consider the equilibrium. And in that case, we have to consider the change from the negative side until the positive phase. In this case, this diagram is just to show you the sign convention that we're going to employ, okay? So we should cross all of these, the changes out, okay? Isaac, are you listening to me? Isaac?
Yes, doctor.
Would you please ask the one of the assistants, okay, to take this figure, both, reproduce them without these changes, okay? And send them to me. So I need to change this because that's wrong in the class notes, please. Okay, so let's go on. Thank you very much. Let's go on now. So in this case, we said that we're going to work with elastic isotropic material. Okay, so we're going to be below yield point. Okay, so there's going to be a linear relationship between stress and strain, but in this case, we're going to have normal stresses in 2 directions, sigma x and sigma y. We neglected sigma z. Okay, so this is from Hooke's law, but considering 2 directions. Okay, so epsilon x in the case of the plate is not simply this. Is this minus nu sigma y over E. Similarly, this is what we remember. Okay, that's something that you should remember from your solid mechanics class. So we have epsilon, we have C, and here we have sigmas. When I say sigmas, I include sigma and also tau. When I say epsilon, I say the first 3 as epsilon and the last 3 are gammas. This is constant. Okay, so in here, I take the first 2, and these are this. Okay, so if I need to express sigma as function of epsilon, what I can do is I can see that I have sigma y, epsilon, and nu. So what I do is I multiply these nu, and I add them. Okay, if I do this, okay, this term here will cancel that one. And I'm going to have sigma x as function of sigma epsilon x and epsilon y. That's what you have in your class notes. So I can say that sigma x is going to be equal to E over 1 minus nu square epsilon x plus nu epsilon y. Okay, so you can express this, or you can express in the other way. Sigma like this. Okay, that's something that comes from solid mechanics. You learned that in that class. So it's just a matter of remembering. The point is that in this case, we're going to have not one sigma, we're going to have three, 2 sigma normal and 1 tau. So at the end, we're going to have something like this: sigma x, sigma y, and tau xy is that going to be equal to pi by epsilon x, epsilon y, and gamma xy. So here I have this is E over 1 minus nu squared, and here I have E nu over 1 minus nu squared. If we do this for sigma y, okay, what we can do is we can multiply the first by nu and then add. And then we will obtain E nu 1 minus nu squared, E over 1 minus nu squared, and this is 0. And if we do this, it will be 0, 0. Question, what would be here in this space? What we would have here in this space?
G.
Yes. So even though we have 3 constants, E, nu, and G, remember that G, E, and nu are related. So we have only 2 unknowns, really, okay? And we measure those in a tension test. Okay, people, we have a couple of minutes. A couple of announcements. First, the most important, for at least for the rest of the semester, I'll try to ask an assistant to look for in our files. We have the video records from the previous year. So I'm going to ask them to get this video and identify parts of the lectures, and I'm going to post it. And you have to listen to them, okay? Or I can post something to read. And in the next session, at the beginning, we're going to do a quick review, okay? Could be something like what we did today, okay? Asking for the participation of some students, or I can give you a short quiz, no value. I'm not going to give you points for that, but that will tell you if you are working enough or not, okay? So from now on, you either have the class notes, videos, or I can assign something to read, okay? But you have to come to class, preparing the class. Second, on this Friday, instead of the lecture, Isaac is going to lead a lab test, okay? We have already 2 plates. One is aluminum, the other is steel. Steel is simply supported, aluminum is clamped, more or less. And what we're going to do is we're going to apply a force in a very small area, so we could assume as it would be a concentrated force, okay? So we have 4 strain gauges in each one of the plates. So what we're going to do is get everything ready, 0, and then designate a point where we're going to apply the load, and then increase the load and decrease. We repeat it several times to check the repetition. Now, since we have several groups, what we can do is we can get the other group to change the position where the load is being applied. Okay, so each group will have a different set of results. And then with in the next assignment, you will have to analyze those results and compare theory with experiments. Okay. Some will work in the aluminum, clamp it, and the other will work in the steel, simply supported. For that, I would like you to, those who can come, this is not obligatory, okay, who can come, send an email to Isaac saying the number of your group and if you are able to come. Okay, so we can try to organize our work. Okay. Also, unfortunately, I see that there are some students who are not coming, and probably they are going to eliminate the register in this class. Okay, so if your group are for some casualty, it's losing some of your members, you can try to reorganize your group. Okay, but please, I know that it is difficult, but at least try to get somebody to satisfy the requirements. Requirements are that you have to have at least one woman, one female student, and also one student from outside Guayaquil. And the idea is that you integrate, you learn how to work with people from a different environment than yours. Okay, is there any questions, people? Any questions about these announcements? Questions? No questions?
How much time is the laboratory?
I think it will take 1 hour or 1 hour or something, because everything is ready, right? You check the strain gauges, they are already installed. So it's just a matter of connecting the strain gauges to the system. We have in the steel case, we have to install some weights in order to be sure that the plate is really well seated on all the edges, and then just a matter of applying the loads. So it shouldn't take more than 1.5 hours, unless you disconnect something. But yeah. Anything else? Any other question, people? Any other question? No? Then I'll see you Thursday. Remember, tomorrow morning, I will post something for you to either see, read, or do before Thursday class. And at the beginning of that, I will make some questions, and thus I will save us some time in the explanation. I can go a little bit faster than that. And also, you'll have the class notes. Okay, so I'll see you Thursday. Bye-bye now.